Thank you very much. So, good morning, everybody, and let me start by thanking the organizers for the invitation. And it's a great pleasure to come to this very nice and relaxed conference. So, I'm going to talk about large deviations in random matrix theory. Now, before I come to random matrix theory, I want to just cover some preliminaries. Now, I mean, most of you, I mean, all of you actually know this very well. It's just the first exercise in Feller's book. But nevertheless, I'll just go through it just to, at least set up my notations. Okay, so this is very, very trivial stuff. And then I'll come to later part to random matrix theory. So first I'll do on the blackboard these preliminaries, and then I'll switch on to slides. And I should say that some of my talk today might have some overlap with what Anupam talked about yesterday, but I didn't know that he was talking before me, so I didn't have time to change the talk. But okay, but a little bit of repetition is not so bad. All right, so this is just, tell me if you can see it, otherwise I'll write bigger. So I'll start with the classic, simplest example that all of you know of a simple coin toss problem. So I have a coin, unbiased coin. With outcome head or tail. And you toss this coin n times, let's say. So a typical outcome, which I call a configuration, so that will be like, let's say head, head, tail, head, tail, tail, etc. So I have n entries. So this is a typical configuration. And because each tossing is independent and they all occur with equal probability each time head or tail, so therefore the probability of any configuration any configuration is exactly same. All configurations are equally likely, and this is 2 to the power minus n. Okay, that's clear. So in particular, if we look at configuration like all tails, which is the same as all heads, is 2 to the power minus n. Okay, I'll put it number 1. So now, I mean, if I look at a particular observable, let's say, for example, simplest observable is number of heads. So number of heads, of course, it lies between n and 0. So in this configuration, nh is 0. In this configuration, nh is capital N. So this is a random variable. Which fluctuates from configuration to configuration. And these are the two extreme cases where it achieves its values 0 and n. Okay? So let's ask, what is the probability distribution of this random variable? So this is number 2. What's the probability that nh equal to, let's say, given that I tossed my coin n times? Okay? So this is simple. This is just a combinatorics. So basically, how many heads are there out of n? So this is just n choose m. And the probability of each configuration is 2 to the power minus n. So therefore, it's just a simple trivial combinatorial exercise, just a binomial distribution. Right? So from this, you can, so if I plot this object, it's a discrete thing. So m is going from 0 to n. So it has its, basically it will be something like this. Schematic drawing. So first thing you can ask, what is the expected value of nh? So that's just, trivially. So I was told to give pedagogical lecture, so this is really pedagogical. So, so n by 2. And if I look at the variance of this, so that will be just n over 4. Okay? And we all know by central limit theorem that around the mean, so the typical sigma, which is the variance, is n by 4. So sigma scales like square root of n. So it fluctuates around its mean value. Mean value is here. And the typical fluctuation here is of order square root of n. So if I go near the peak and I look at this part of my PDF, then by central limit theorem, we know that you can actually approximate this around that regime by Gaussian distribution. So I don't write the prefactor, just okay. So this is the mean, this is the variance, and it sort of locally, if I zoom in here, I should see a Gaussian distribution. Now, the point is that this is valid for typical fluctuation. When m minus average value of m, which is n by 2, this is of order, let's say, root n. That is this part of your PDF. Okay? But if I go far away from this central peak, then this Gaussian approximation is no longer good. And this is to see that. So suppose I take this Gaussian form, and suppose I want to look at this probability. What's the probability that nh equal to 0, which means m equal to 0. So if I just put m equal to 0 here, so you see that this will be just, 2, n by 2. For large, okay, there's some prefactor, but let's not bother about that. So the large n limit, this leakage is like exponential minus n over 2. But the exact answer it's actually exactly equal to 2 to the power minus n, which is e to the power minus n log 2. So log 2 is about 0.69, and this is about 0.5. So you see the actual answer, so the real curve is here, but if you take the Gaussian approximation, I mean schematically, it will come here. It will overestimate the probabilities at the tails. Okay? So therefore, I mean, this form is not valid everywhere. And so to get the tails, the extreme probabilities, so you need large deviation. And so again, this is, all of you know this, but just to set up my notation. So, so to capture the tails, central part as well as the tails, the full curve, if you like. So what you can do, you can set, so I take this exact, in this case I know exactly what the probability is. This is this guy here. So I can set, because I'm now looking for fluctuations not just of order square root of n, but I'm looking for fluctuations of order n. Okay? So, so therefore you can set m equal to some c times n, where c is a fraction of positive heads basically, and it varies between 0 and 1. So if I take this expression here, and I put m equal to cn, n, so this is n factorial over cn factorial 1 minus c times n factorial times 2 to the power minus n. And if you use this Starling approximation, now I'm taking the large n limit, keeping c fixed. So Starling approximation tells you this goes like e to the power n log n minus n to leading order. So if I just put it back there, and just simple exercise will tell you that this is of this large deviation form, and where this phi of c is the rate function, which is just c log c plus 1 minus c log 1 minus c minus log 2. Okay? So once we have this form, then first thing, you can check that as C goes to half, so if I just expand this in Taylor series around C equal to half, so then the phi C is just 2 times C minus half square. So if I put this phi of C here and just write C equal to M over N, you get back the central Gaussian form. So recovers the typical fluctuations. In contrast, if I put C close to 0 or 1, it's a symmetric curve. So let's say C goes to 0. So from here you see that you get back correctly the log 2, and therefore it's e to the power minus n log 2, which is indeed the exact answer, 2 to the power minus n. Okay. So this is the thing. So large deviation, basically main point is that large deviation actually captures more or less the full curve, especially when you have different length scales in the problem. In this case, the fluctuation scales are square root of n and n. But one thing that we see from this simple exercise is that this phi of C, so if you plot this function phi of C versus C in that many times, so it goes like, so it's a smooth function with a quadratic parabola here around C equal to half, and it approaches to this number minus, okay, so this is plus log 2 or minus log 2. Sorry, this should be plus log 2, yeah. So this is log 2, this is log 2, okay? And it's a symmetric around C equal to half. Okay, so this is the trivial exercise that we all know. Now this, the way I derived it is, of course, just simple combinatorial exercise. But let's try to derive exactly the same result, same problem, but a little bit algebraically, because that will be useful when we go to okay, so generally, so let's say our outcomes, so let me call xi, which in this case is either head or tail. Okay. And let me sort of assign a scalar number. So let me call head is like 1 and tail is like 0. Okay, so my outcomes are either 1 or 0 each time I toss the coin. And so this, any configuration is specified by these variables x1, x2, x3, xn. Now in general, okay, in this particular case, we'll write. So in general, these are random variables, and let's say they are drawn from some joint distribution. So called joint probability density function, JPDF, all this of these random variables. Now in our particular example, this is very simple because here, because this is independent variables, xi's are independent, so it's actually product of individual variables. So it factorizes into n individual probability distribution, where this little p of x is just half delta x plus half delta x minus 1. Because with probability half, it's 0. With probability half, it's 1. So this is the px. Okay? So this is the example. So given this joint distribution, or more precisely, this particular factorized form, what we are interested is the number of heads. So what is number of heads? So number of heads is just theta of xi, where theta is a step function. So theta of x is 1 if x, my convention is strictly positive, and is 0 if x is less than or equal to 0. So nh is just, it just counts the number of sorry, number of heads it should be. Yeah, it just counts the number of heads. Whenever xi is positive, it just counts, otherwise it gives you 0. So for any given configuration, this just gives, this is a random variable and it gives me just the number of heads, okay? So this is an example of what we call generally the linear statistics. So in general, I could put any function here. This function doesn't have to be necessarily linear. Linear statistics means that basically, same function appears for each xi isotropically. And in this particular example, fx is just a theta function. Okay? But in general, you can say that I'm interested in the linear statistics of some observables. So let me see. I want to use the same notation for everything. So yeah, let me call it in general this m. Okay, so this particular case is just the theta functions. Okay? So the general problem is that you have a joint distribution. You give me the joint distribution, and I want to calculate the distribution of this linear statistic. So you give me the joint distribution, you give me the function f of xi. It could be, for example, linear function, just sum of random variables, or it could be xi square plus x1 square, x2 square, fx is square, whatever, I mean, any function that you like. And you would like to compute. So the general problem is the following, and I'll give an example of this. That specify the joint distribution, which need not always factorize. Factorize is the only independent case. So you give me this, and you give me the function fx, this linear statistics. So m equal to f of xi. And I want to compute the probability distribution of m given n and given f and b. Okay, so that's the general problem. Of course, in general, it's a very hard problem, but we'll see some examples in a minute. But let's just recover our old result in a little bit algebraic way. Again, you have seen this. So I want to calculate this object, particularly this number of heads. Okay. So how do I calculate this? P of mn. In general, so what is it in general? So I have this joint distribution of these variables. I want to calculate this probability. So all I have to do is to stick in a delta function and put m minus summation f of xi integral over dxn. Okay? So that's the problem. Of course, the main problem is in general, when it doesn't factorize, it's very hard to do this multiple integral. Okay? Now, the first thing, of course, you can do, so exactly just to recover our result, so in our particular special case, so there it factorizes, so I have product of p of xi, where p of xi is, whatever, half delta function, blah, blah, blah. So this is the object I want to calculate. So as you know, I mean, first thing to do is to, because here m is a discrete variables, so you can look at the generating function of this object. So this is written in this notation. M is a random variable, so z to the power m, this cumulant generating function. So this immediately tells you that this is p of xi, z to the power sum over theta of xi. So this is the crucial simplification, because if you don't factorize it, you can't do anything basically at least at this stage. And once you have this, so then you see that this just becomes the same object, p of x, z to the power x dx integral over n. So in our case, p of x is half delta of x plus half delta of x minus 1. So if I just plug it in and just compute this whole thing, this is just 1 plus z by 2 to the power n. Okay? So all I have to do is to expand this in a power series in z and read off what is p of mn. And we know this, when we expand this in power series in n, so this is just a binomial. And this then sort of we recover the result that we wrote combinatorially, namely the binomial distribution. Okay. So, okay. So in this particular case, you can see example that you can actually explicitly do this computation, but in general, when this doesn't factorize, okay, so it's a little bit harder to do that. So, of course, one thing you can do for the general case, okay, let's first give an example of a general case. So, simplest example that you can think of, if you come from statistical mechanics background, imagine that this x size represents the positions of a gas or particles on a line, in one dimension, but you can think of higher dimension also, it doesn't matter. So I have a set of particles which are on a line, and these are the positions of the particles. And imagine that there is an energy function associated with each positions. This is the first thing we learned in statistical mechanics. So maybe there is a confining potential which confines all these particles in a limited region of space, in general. Some potential they are filling. Plus there's an interaction term. So let me write it this way. So this is an interaction between ith and jth particle, and this is the external potential that all the particles fill. And Ising model, you can write it this way if you think of these xi's as discrete variables on a lattice, and so on. Now this ij, this sum, it can go, for example, just over nearest neighbors, okay, in the label space. So, for example, if it is just ii plus 1 or ii minus 1, if it extends only over 2 indices, then this is, for example, just a short-range nearest neighbor model. Okay. So you can have a range of interaction, so which just goes up to neighbors, let's say fifth neighbor or something. So then it's it's a short-range interaction. On the other hand, if this ij extends over all, I goes from 1 to n, and j goes from 1 to n, then this is like a mean field model, totally long-range interaction. Everybody is interacting with everybody. So, a whole class of models, in just fluids, spin systems, everything you can sort of generically write the energy of a configuration like this. And so then, given this, and imagine that now the system is in thermal equilibrium, so therefore the probability of a configuration C is just 1 over Zn exponential minus beta, the energy of this configuration, where beta is this inverse temperature. So this is the Boltzmann distribution, and Zn is the partition function, which is just this integral of okay. So then you see that this and Zn is just normalizes this probability distribution, and I'm assuming that V, the potential, and G are such that this integral, this is normalizable basically. This integral exists. So once you have that, then you see this is a particular example of this general P of xi. And here, of course, if there is no interaction, if this G is 0, it's a non-interacting system. In that case, the P of xi again factorizes. So okay, I can write it as little product of xi, where px is just proportional to e to the power minus beta p of x. Okay, but the moment you have non-zero interaction, this factorization no longer works. So this is an interacting system, and so the linear statistics of interacting system is what I'm interested in general. So you'll see later when I come to random matrix theory, there, these xi's will be the eigenvalues of a random matrix, and you can again cast this problem exactly this way, where this Vx is some matrix potential, and this G, there it will be some log interaction, Coulomb interaction. So in that case, it's a totally long-range system, okay? And so the physics of short-range system that we are familiar with will no longer be applicable. So the large deviation principle, so again, why large deviation? Because, okay, so imagine that you give me this probability distribution, and now I'm interested in the linear statistics, which is this object. So for instance, I could choose the function f of x to be just x. So in that case, m is just the sum, which is basically the center of mass. So this is just n times x bar, where x bar is the center of mass of all these particles, okay? Or I could choose the theta function that I'm using. So theta function, if I use, this just indicates the number of particles to the right of the origin. And so it's a random variable. It fluctuates from configuration to configuration. And I'm just interested in the distribution of this object, P of Mn. So that's the problem. So we have seen that for the simplest example, when things factorize, then you have a simple large deviation form, which is e to the power minus n into some function of m over n. So this is but the moment you have interaction, in particular long-range interaction, short-range interaction will more or less behave like the non-interacting system. But if you have a long-range interaction, which is the case in random matrix theory, as we'll see, this large deviation principle completely changes. You will see different speed which will appear in the prefactor and different types of large deviation function, some of which Anupam mentioned. But so that is the sort of general problem. Okay, so we are interested in the interacting particle system with some typically long-range interaction. And so I know what is exactly the probability distribution of the configuration. And given that, and given this f of xi, we'll see several examples as I go along. And I want to calculate P of Mn. And what can I say about this? Okay, so this is the problem. Now, before I come to this general linear statistics, I want to sort of go back to this question number 1 here, which is a special case. In this case, you can see this is a large deviation question because this is a tail event of this distribution. What's the probability that all the outcomes are tails? And here it's 2 to the power minus n. And we'll ask a similar question in random matrix theory. And so I'll discuss that first, and then I'll come to the question of the number of positive eigenvalues or number of negative eigenvalues, which are known as the index problem in general. Okay, so is there any question? I'll now move to the slides. Well, you'll see how it comes out actually. So yeah, it is a mean field theory actually, because long-range interaction mean field theory is exact there in the large n limit. Okay, so in fact, what happens here, you will see that when I go into the continuum limit, it's actually only the energy term which contributes, which is typical of order n square because all particles are interacting with each other. And the entropy term will be of order n. And so essentially all you have to do is to minimize the energy. Okay. And in the large n limit, it's exact. Okay, so before I give you the motivation why the large deviation question is interesting in random matrix theory, but before I do that, before I talk about the top eigenvalue, etc. So let's start with again, I just want to connect up with this story here. So let's start with a very, very simple example, okay? So it's just, again, a trivial problem. So imagine that you have a matrix, okay, n by n, but it's a very simple matrix. It's a just diagonal matrix, okay? So diagonal matrix, these are random variables, the diagonal elements, and I choose them from a Gaussian distribution, simply with variance 1, okay? Very, very simple. And suppose I ask this question. So, this is a trivial example. So there are n real eigenvalues, of course, which are just these elements themselves because the matrix is diagonal. Okay. So this trivially, these lambda i's, they are totally independent. So this is exactly this factorizable case here. Okay. So the joint distribution of the eigenvalues is just the product of these guys, and so it's just an independent variable. And if I ask now, what's the probability that all the eigenvalues are negative? Okay. So this is exactly analog of this, what's the probability that all are tails? Okay. So trivially, because you say Gaussian, but you can take any symmetric distribution. So this will be the product of that each of them is negative, and each of them is negative is just half. So it's 2 to the power minus n. So once again we see that it decays like exponential minus log 2n. Okay, so this is trivial. Now let us take the same real symmetric matrix Jij, except now that it's no longer diagonal. And you have each entry, so it's symmetric. So I choose each entry independently from a Gaussian distribution. So like this, P of j. And so now there are n real eigenvalues. I diagonalize. For each realization of these random entries, I can diagonalize. I'll get n real eigenvalues because this is a real symmetric matrix. So I'm guaranteed that all the eigenvalues are real. So I get n real eigenvalues. But the problem is now is that these eigenvalues are strongly correlated, as we'll see. Okay? And if I ask this same question, that what is the probability that all the eigenvalues are negative? So notice that this is the same question as the probability that the largest eigenvalue is negative, right? Because the same event, if all the eigenvalues are less than 0, so necessarily lambda max, maximum of them is less than 0. And similarly, if the largest eigenvalue is less than 0, that means that all the eigenvalues have to be negative. So this event here is exactly the same event as this. Okay? Now this simple question, a very simple question, right? You can just do it on your computer in 2 minutes. Okay. So now this has a long history. It appeared in so many different problems in different disguise. Okay. The first, it appeared in a paper by Robert May in Nature in 1972 in the context of population dynamics in ecosystems. Then in the spin glass systems, Juan here with Andrea Cavagna and Irene Geratina, they had looked at, not exactly this question, but they were looked at this problem of index problem in the spin glass context. And then, many other people. And then in the string theory and cosmology, exactly same question appeared, okay? And then in mathematics, in the random polynomials and so on, I'll not go into the details of this. But essentially this fundamental, this basic question, which appeared in different contexts, in different, different fields, okay? So what can we say about this? Okay. So let's see. So let's just start with a simple example. Okay. So I want to calculate this. So let's take simplest example, n equal to 1. So you have just one random, 1 by 1 matrix, so just one element, and it's a Gaussian distribution. So what's the probability that it's less than half, less than 0, negative? It's just half, right? So it's 0.5 trivially. Now if you look at n equal to 2, so it's a 2 by 2 matrix with the Gaussian entries, and you just diagonalize, and you look at the event that both eigenvalues are negative. You can compute. It's not too difficult. It's a little bit algebra. You can compute, and it turns out to be some number like this, 0.146. Okay. N equal to 3 already is rather complicated, and it was actually calculated quite recently, 10 years back, basically. Before that, it was not possible to compute this. And this number is, so it decays quite, as n increases, it decays quite rapidly. And so, when I started working on this problem, so it was not known what is the large n behavior of this. Okay? The question is, how does Pn decay for large n as n goes to infinity? So recall that in the case of diagonal thing, that is when the factorizable case, it was decaying as exponential minus n log 2, right? So, but here, you'll see that the answer will be different. In fact, okay, I'll just tell you a little story. So, in fact, in 2006, we were in, that time I didn't know anything about random matrix theory. So I was in a workshop in Newton Institute in Cambridge, And so we heard many talks on out of equilibrium systems and just got bored at some point. And just walking around the corridor, myself and my friend David Dean. And so we walked into a string theory talk by this gentleman, Richard Esther from Cornell. And he was giving this talk. And basically, essentially in the end, he was asking this question, precisely the same question. And so they, looked at numerically and found that the Pn decays as exponential minus n square, okay? With a number here, which they computed numerically as 0.27, okay? So of course, it's a very, very small probability. It's much smaller than exponential minus n. It goes like n squares. And so first thing we wanted to know that why is it n squared? I mean, it will be obvious when I come later in retrospect, but at that time, it was not obvious to us that why should decay n squared, because your normal intuition always says that it should go like m e to the minus n. So we wanted to understand that, and also we want to know if we can calculate this number theta, okay? So we said how difficult it can be. But, well, it turned out to be quite difficult at the end. So in the end, I'll show you that you can compute this number theta exactly, and it turns out to be just 1/4 log 3, which is quite in good agreement with this numerics. So I want to first show you why this is a large deviation question. And then I want to tell you that, I want to put this problem in a much sort of bigger context to see. But let me first just take, I told you that it appears in many different systems. So let me just give you one example of the context in which this question appears naturally. So in many problems in statistical physics, we know that the complex landscape plays a very important problem, like structural classes, supercooled liquids, spin glasses. In string theory, this is a string landscape. So for example, in glasses, this is the configuration of your particles, for example, hot sphere particles, and this is the energy. And so in general, this is a very high-dimensional space, multi-dimensional space. Okay, this is just a cartoon picture in one dimension. So as you change the configuration, the energy, is a complicated landscape. And with lots of local minimum like this. There's a global minimum here, but there are lots of local minimum. And as you know, in glassy dynamics, the system under its normal dynamics, it moves from configuration to configuration. Then it might get stuck in a local configuration like metastable state like this, and then it takes a long time to go over the barrier and come to the next local minimum, and then eventually might be the global minimum, but it can get stuck for a very, very long time because if this barrier becomes very high, it cannot go over essentially by thermal fluctuation. So it's quite important to understand the statistics of the stationary points, that is the local minima and local maximum, or in general in multi-dimensional space you'll have saddle points of such complex landscapes. And this has been studied ad infinitum. In this context of string theory, so this configuration is what is called the moduli space. This is called the moduli space. So you have different constants and coupling constants, for example, gravitational constant and so on and so forth. So one of the questions that the string theorists were interested in, that if you look at, so imagine this complicated coupling space, you have again a landscape, and our universe is sitting somewhere. Now so their motivation was that following. So you can ask this question that when you see, for example, the gravitational constant, okay, so gravitational constant has a unique value. Okay, or Newton's, gravitational constant, whatever, or charge of an electron. Okay, it has a unique value. So these constants, so how come they are unique? Why? What made them select these particular values, and why not some other value? Okay, so the argument, okay, it's a bit philosophical argument in my opinion, but they call it anthropic landscape string theory. So their argument is that that maybe in this complicated moduli space, so each point is a possible universe, and so our universe is actually sort of maybe the global minimum in this complicated space. And if you are sitting in this minimum, its associated gravitational constant and everything has this unique value. If you are sitting in another minimum, you would have a different gravitational constant, different electric charge, and so on. But so somehow that our universe is unique in the sense that maybe that there is only very few global minimum in this complicated landscape, and so they were interested in precisely computing the number or the fraction of such local minimum, for example, I mean, and so on. So that's the sort of, you can read these are two articles, quite interesting actually. So anyway, so this is the general motivation. So let's take a simple example. So imagine that I have an n-dimensional landscape. So it's a potential. So y1, y2, y3, yn. So these are the coordinates in the n directions, if you like. And so now a particle is basically your system, which is moving in this complicated landscape. And let's think of a simple dynamics, which is just this, just this steepest descent dynamics. So dy dt is just minus grad v. Okay. So stationary point means that the gradient of v is 0, right? So at some stationary point, y equal to y stars. So those are the local minimum, local maximum of the saddle points. And so near a stationary point, you can linearize your potential. And so linear term will be 0, of course, because the grad v is 0 at the stationary point. So you have to go to the second order term. And if you go to the just Taylor expansion, second order term, so you see this is the Hessian matrix, which is the second derivative of this potential. Okay, so locally, I can look at my potential as a quadratic potential near a stationary point, and the coefficients of the directions are just this Hessian matrix. Okay, so the eigenvalues of this Hessian matrix, so this is called the stability matrix. So they determine the nature of the stationary point, whether it's a local minimum or a local maximum or saddle point, right? So for instance, I mean, let's look at this. So imagine that I have just one-dimensional interface, one-dimensional landscape. So then the Hessian matrix is just del 2 v del y square. So you all know that if it is a local maximum, second derivative is negative. And if it is a local maximum, local maximum is second derivative is negative. And if it's the local minimum, second derivative is positive. Okay. So in this case, it's a 1-by-1 matrix, this Hessian matrix. So whether it's positive or negative, that determines you have only two possibilities, either a local maximum or a local minimum. Okay. If you take a two-dimensional surface, n equal to 2, so Hessian matrix is a 2-by-2 matrix. Okay. So in this case, I can diagonalize this, and it's a symmetric matrix, real symmetric matrix. So I can diagonalize, I get two real eigenvalues. So if both eigenvalues are negative, I have a local maximum in this two-dimensional space. If both are positive, I have a local minimum. And if one of them is positive and the other is negative, or vice versa, you have a saddle point like this. Okay. So your configuration is moving in this multi-dimensional space, and so there are these local minimum, local maximum, and saddle point. Now, before even and if it comes to a local minimum, it can stay there for a very long time, and those are the metastable states. So first thing you want to know the statistics of these stationary points. How many such local minimum are there? How many local maximum are there? And how many saddle points are there, right? So of course that depends on how you model your landscape V. So the simplest model is called this random Hessian model. So this is not a very realistic model, but at least it gives you a lot of insights. So imagine that. So all I know is a real symmetric matrix, and I just assume that this this is just a Gaussian matrix. Okay, random. All the elements are random, and they are it's a symmetric, real symmetric Gaussian with Gaussian entries. So this is, we'll see in a minute. This is what is called the Gaussian orthogonal ensemble, and again, this was first sort of studied in this context by Cavagna, Garahan, and Giardina, and then later, as I said, string theorists were studying exactly the same model. So you ask, okay, given this Hessian model, random Hessian model, what is the fraction of local minimum? What is the fraction of local maximum? And what is the fraction of saddle points? Okay. So to compute that, so let's say Pn is the fraction of local maximum. Okay. So that means this is just exactly given this random matrix, what is the probability that all the eigenvalues of this Hessian matrix are negative, right? Which is exactly the same event as the probability that the largest eigenvalue is negative. So the fact that for this real symmetric Gaussian matrix, this guy decays as exponential minus theta n square, which means that this is actually very, very small. So that means if you look at your landscape and you look at the fraction of local maximum or local minimum, because this is identical symmetric, so they are extremely tiny. 99.9% of the stationary points are actually saddle points. Okay, so there are very few local maximum or local minimum. So this actually made the string theorists happy, because they said, well, that means that just shows that maybe that there is only one minimum in this whole landscape, and that is our universe. It's unique in that sense. Okay, so anyway, this was the string theory motivation. But anyway, so this is the sort of result, and we wanted to understand this result. Okay, so how to how to calculate this, how to prove this result, and what is the value theta here? Okay. So most of the stationary points are saddle points in this random Hessian model. Okay, so let me now put it in a more general context of random matrix theory. I'll just give a brief introduction to random matrix theory. I cannot go into all the details, and then we'll see why. Because for the moment, when I state this problem like this, you see, it's not obvious to me, at least to me, that this is a large deviation question. Okay, and we'll see in a minute why this is a large deviation question. So let me start with just remind you some basics of Gaussian random matrix theory. So random matrix theory was actually first introduced by John Wishart. He was a statistician in Cambridge, first in Edinburgh and then Cambridge, in 1928, in a paper which was published in Biometrica. And he was a statistician, and he was interested in the data analysis of certain covariance matrices and so on. But and then later it was taken up by Wigner, Dyson, and many others in the physics community because they came from nuclear physics motivation. And but I will not go into the history, just to tell you just the basic problem. Okay. So what we have is again a n by n matrix, and with random entries. Okay. And I'm interested in, for the moment, in random matrices with real eigenvalues. Okay. So what are the matrices which can give you real eigenvalues? So of course, if it is a real symmetric matrix, we all know that it has all the eigenvalues are real. If it is a complex Hermitian matrix, like in quantum mechanics, then again, you know that all the eigenvalues are real. And there is yet a third class, which is called the complex quaternionic, which also has real eigenvalues. Okay? And so if you ask, what are the classes of matrices which have real eigenvalues, then, this is called the Dyson's threefold way. So Dyson actually proved that, there are only these three types of matrices which have real eigenvalues. Any other matrix you can construct, it will have complex eigenvalues in general. Okay? So we'll restrict to these particular Dyson classes, and then you want to specify from which distribution you are drawing your entries. Okay? So that is called the matrix model in general. So the simplest matrix model is that I specify that these entries are drawn independently from a Gaussian distribution with a certain variance, which I choose for the moment to be some number beta. We will specify this beta later. And also as n, you will see a reason why I'm choosing scaling it by n. And I write it this way. And notice that, here it's a sum over all ij. Now j12 is the same as j21. So that means these guys, they have a variance which is half that of the variance of the diagonal elements. Okay? Now, why do I do that? Why do I choose these particular special variances? Because if I write it this way, then I can actually, this object here is just a trace of j dagger j. J is this matrix, okay? Now, what is the advantage of that? The advantage of that is that, you see this, when I'm able to write as exponential minus trace of this j dagger j, then if I make a rotation, for example, for the real symmetric matrix, if I make an orthogonal rotation, okay, I change the basis. Okay, so under orthogonal rotations, the trace of j dagger j is invariant under such rotation, right? So because this is just the same object basically. Trace of this is the invariant under rotation, and similarly, with the complex Hermitian case, this is invariant under a unitary rotation by j. And in this case, it's it's something called symplectic ensemble, symplectic rotation, basically. Okay, so I'll not go into the details, but you can see. I mean, main point is that why in nuclear physics, why Dyson was interested in this, because in nuclear physics, I mean, essentially the main idea is that you are representing a complex Hamiltonian of your nuclei, which has lots of protons and neutrons. They're interacting with each other, so we don't know exactly the nature of the interactions. So what Wigner said is that okay, let's replace it by just a random matrix, the Hamiltonian in some basis. So this is just a Hamiltonian in a certain basis. But then Hamiltonian, the spectrum of this should be invariant when you make the rotation, right? If you choose a different basis, we know that in quantum mechanics, the eigenvalue should not change. And so that was the reason why that the entries should be such that it's invariant under a change of basis. Okay, so that was the original motivation. And And so for these three classes with real eigenvalues for the Gaussian matrices, you see there are they are invariant under these three types of rotations, and that's why it's called the Gaussian ensemble, Gaussian orthogonal ensemble, Gaussian unitary ensemble, when this is a complex entries, complex Hermitian matrix, or in case of quaternion unique, it's called the Gaussian symplectic ensemble. Okay, so this is the basic definition of Gaussian ensemble. Okay, so you specify, once you have specified the distribution of the entries, so now I diagonalize this matrix, and I get n real eigenvalues. And so we'll see in a minute that these eigenvalues actually happen to be very strongly correlated. Okay, and the whole game of random matrix theory is to understand the spectral statistics of these eigenvalues. You know, what can we say about the statistics of these lambdas? Okay, so this is all about random matrix theory essentially. So let's see what we can say about this joint distribution of this. So the problem is very clear, right? So you give me the entries, you have given me the joint distribution of the entries. So joint distribution of the entries is very simple. It's it's a product of Gaussians, and I want to know what is the joint distribution of eigenvalues. Okay, so this is actually a very difficult problem. It's not easy, and so Wigner, maybe before that even Porter Thomas and other people, so they were able to compute the joint distribution of the eigenvalues starting from the joint distribution of entries. Okay. And the answer is here. So what you see is that the first term is just this guy here, because if I write in terms of eigenvalues, you know, this is just summation lambda is square. It's a trace of j dagger j. So this part actually just comes out. So how do you solve this problem? I mean, just to say, I won't go into the details, but just to give you an idea of what you do actually to derive this. This is a non-trivial derivation, but it's nice, and one should learn this because it's very, very instructive actually. So the idea is that, okay, so I have let's say real symmetric matrix, okay? So how many entries are there? How many independent entries are there? So 1 plus 2 plus 3 plus up to n, right? Because these guys, this is a real symmetric matrix. So once I've chosen these elements, these are automatically chosen. So the independent number of degrees of freedom is just 1 plus 2 plus 3 plus up to n into n plus 1. So I have a number of degrees of freedom, which is n into n plus 1 over 2. And I know the joint distribution of these degrees of freedom. Okay. So I want to calculate the distribution of the eigenvalues, the joint distribution of the eigenvalues. So basic idea is to first make a change table. So you have these entries, xij, with so many independent guys. I want to make a change of variable to another set of coordinates. Now you can choose whatever you like, but since you are interested in the eigenvalues and eigenvalues, so what you do is you actually choose the n eigenvalues as one set of degrees of freedom. Now how do you diagonalize it? So if you have this matrix X, you just do S transpose X, right? So this is your diagonal matrix. And we know that this vector S, this matrix is, its entries, the columns, are the eigenvectors, right? Now, how many independent degrees of freedom are there in the eigenvectors? Okay. So what are the relations? Eigenvectors, they are orthogonal to each other, and they are each normalized to 1, right? So if you count the number of independent degrees of freedom in the eigenvector, so this is actually, you can check that this is n into n minus 1 over 2. Okay. So I have the n into n minus 1 over 2 eigenvector degrees of freedom. So the total, here you have n, and here you have n into n minus 1 over 2. So when you add up, this is exactly n into n plus 1 over 2. So this is actually a good, basis to change from. So I want to go from the entries to eigenvalues and eigenvectors, okay? So I know the joint distribution of this. So from that, I can try to obtain the joint distribution of eigenvalues as well as eigenvectors, okay? And then I want to integrate over the eigenvector degrees of freedom to obtain the marginal distribution of the joint distribution of the eigenvalues, okay? So that is the program basically. And so what happens with the so you can see that when you make this change of variable from this set of coordinates to that, there will be a Jacobian term, okay? So this guy here, this additional term here, which appears, this is precisely the Jacobian term. Okay? And for rotationally invariant ensembles, what happens is that I'm just not showing you explicitly, I'm just telling you that these eigenvalue degrees of freedom, they get separated from the eigenvector degrees of freedom. So you can forget about the eigenvalue, just integrate over the eigenvectors quite easily, and you just get the joint distribution of eigenvalues. So of course, in this joint distribution, so figuratively what you are doing is P of xi, dx1, dx11, etc. You are going to P of lambda I into the eigenvector degrees of freedom, Sij's, and then you have this d lambda 1, d lambda n, ds1, 1, etc. Okay? And then so they decouple, and you integrate over the eigenvector degrees of freedom, and all you are left with is just the joint distribution of eigenvalues plus a Jacobian from the transformation. And so this is the precise, to compute this Jacobian is not completely trivial. You should do the exercise with just a 2 by 2 matrix. It's quite instructive. So I won't give derivation, but this is the sort of classical result of random matrix theory, that there's a Jacobian factor which comes in. So the point is that this Jacobian factor, which is called the Vandermonde, for a reason which will be clear in a minute, and this is the normalization constant, which is just this integral. We call it partition function. And so the point is that if you did not have this factor, okay, so let's see if I have another slide here. So, this term here, okay, makes the eigenvalue strongly correlated, okay? Because if I did not have this term, again, you see that this will factorize. And if you ask what's the probability that all the eigenvalues will be negative, again, it will be 2 to the power minus n. So it's this guy here which makes the problem, non-trivial because of the correlation between the eigenvalues. So what you see, and here there's a number beta which appears, and this beta is 1 if you are a real symmetric matrix, that is Gaussian orthogonal ensemble. It's 2 if it's a GUE, and it's beta equal to 4. So these are called the Dyson indices. Okay? Nowadays, one knows random matrix ensembles where you can even have a continuous beta, but classical Gaussian ensembles, you have just these three quantized values of beta when you calculate the joint distribution. Okay? And now the reason I scaled my lambdas with a variance which is proportional to beta is obviously because I want to write this object as e to the power beta log of lambda j minus lambda k, so that you can interpret this beta as, okay, it's behind this thing as a Boltzmann factor, and then you see that this problem exactly becomes analogous to one of these special cases of these general interacting gas problem. Okay, so we'll see that in a minute. Okay, now before I do that, before I talk about that this is a sort of interacting Coulomb gas in 1D, I just want to show you one physical realization of the eigenvalues, because this is a very mathematical thing, right? You give me a matrix and with random entries, and you're asking me to calculate the eigenvalues of this. Now, okay, can we sort of realize this, let's say in a real experiment, okay? Where these lambdas have real meaning, and what is the origin of? So here you see that because of this term, the eigenvalues repel each other. So the probability that two eigenvalues are very close to each other goes to 0, okay? Because of this interaction term, they repel each other. And this is what is called the eigenvalue repulsion nuclear physics. This is what you see in nuclear physics. And that's why this Wigner's theory was extremely successful to explain the level repulsion in nuclear spectra. So now here you see the origin of this term, this repulsion term, is purely mathematical. It just comes from a Jacobian of the transformation. Okay? Now I want to first give you an example of a real physical example where this will appear very naturally. And this is actually quite nice. Okay, so let me just explain to you, and then I'll come back to this joint distribution. So what's the physical example? So yesterday Andrea was talking about cold atoms. So you all know that these days you can manufacture cold atoms in the laboratory by creating laser traps, which is basically a harmonic trap, and you can trap the atoms in this harmonic potential. And you can pretty much do anything. You can put many bosons or fermions. You can tune the interaction using what is called the phase-back resonance. And you can do many things. It's amazing what they can do, okay? So I want to look at just n free fermions in a harmonic trap. But before that, let me just, since it's pedagogical, let me remind you just, clear class 10 quantum mechanics course. So this will be a physical relation of GUE eigenvalues. So imagine that you have just a single particle, quantum mechanics, okay, in one dimension, in a potential half m omega square x square. And I want to solve this Schrodinger equation, right? So you just put it there. So epsilon k are the levels. And I put the boundary condition that phi k should vanish at plus minus infinity. So we know how to solve this problem. We have all learned. So this is just single particle eigenfunctions are just Gaussian times Hermite polynomials. Okay, so Hermite polynomials are just h0x is 1, h1x is 2x, 4x square minus 2. And this alpha here is just the length scale, inverse length scale. This is just m omega by h bar. Okay, so this is just the width of the ground state wave packet. So if I put k equal to 0, the system is in ground state. And you know, ground state, it's not a delta function. It still has a Gaussian form. It still has some spread. And that is because of the quantum fluctuation of the particle. And so even in the ground state, a single particle will have fluctuations. And this is sort of, the scale of this fluctuation is just 1 over alpha. Okay, so this is basic quantum mechanics. So now I want to put n such free fermions, okay? Free in the sense that, there is no direct interaction between them, but they're still fermions, meaning that they satisfy the Pauli exclusion principle, okay? So I want to construct now the many-body ground state wave function. So I want to know this system, the ground state wave function of this many-body system. So now my Hamiltonian is just the sum of the single particle Hamiltonians. I want to construct the many-body ground state wave function. So how do I do that? So again, we have learned in our basic quantum mechanics course that you have to construct by this later determinant. That means you have to construct an n by n determinant whose entries are single particle wave functions. And these are the single particle levels. So you take your n electrons and you put one. You cannot put 2 electrons in the same level because of Pauli exclusion principle. So you have to construct put the electrons up to the Fermi level, 1 in each level. So you go from k equal to 0 to k equal to n minus 1. And by construction, you see whenever xi equal to xj with I not equal to j, this determinant vanishes because the 2 rows will be identical. So that's why the wave function vanishes whenever any 2 coordinates become equal, and that's the sort of Pauli exclusion principle. Okay. So this is the sort of unique ground state in this problem because the single particle wave functions are unique. And so let's see what it says. So I want to know, calculate this wave function. Okay. So what is the single particle wave function? This is Gaussian times Hermite polynomial. So when you put this Gaussian, just work it out by 2 by 0, 3 by 3 example, factors, they all come out of the determinant. So what you are left with is determinant of a Hermite polynomial. Okay? Now, determinant of a Hermite polynomial, you can always express it as a Vandermonde determinant. I'll show you an example in a minute. And you can show that this is just a product of xj minus xk, j less than k. So how do I show this? Just to give you one example. Okay? So let's take n equal to 3. So I have a 3 by 3 matrix. So the Gaussian factors have gone out. So I have just a Hermite polynomial. So first particle is at 0th state, so h0x1. Then h1x1, h2x1, and h0, h1, h1, etc. Okay, and these are polynomials, Hermite polynomials. So I put these values here. So you see this is of this form. But then I can just multiply this row by 2 and add to this, and I can just take out these 4 factors, and you just do this just a row column addition and interaction, addition and subtraction, and this immediately reduces to the Vandermonde form. Okay? And the Vandermonde determinant, you can evaluate it explicitly, and this is just x1 minus x2, x2 minus x3, and you can generalize this to n case very easily. Okay. So let's go back to this then. So therefore, the determinant of this polynomial is just xj minus xk. So this is my ground state many-body wave function. So quantum fluctuation is specified by wave function mod square. So you can interpret this as a probability density function because it's normalized to 1 and it's positive everywhere. So this just sort of typifies the quantum fluctuations in the system. So what it says is that the ground state quantum fluctuation, or PDF if you like, of the quantum fluctuations is precisely given by just the Gaussian times this xj minus xk square, Vandermonde square. Okay? So this is, but you remember this is exactly the GUE eigenvalues for with beta equal to 2, right? So let's look at these two problems. So for the fermion, ground state wave function square is of this form with alpha equal to square root of m omega by h bar and xj minus xk square. Whereas in the GUE eigenvalues, GUE, that's why the beta equal to 2. So you see that this is, again, this is the Gaussian form and times the Vandermonde square. Okay. But the nice thing about this exercise is you actually understand where this guy is coming from. Okay. This comes from Pauli exclusion principle. This tells you that two electrons cannot be in the same position in space. Okay. The probability for that is 0. Okay. And you see how it comes out. And so what you have is there's an exact one-to-one correspondence between the positions of the free fermions on a 1D line in harmonic trap to the eigenvalues of the GUE. Okay? So this is a beautiful physical relation, and in fact, this sort of gives you access because of the cold atom experiments now. In fact, we are discussing with Christoph Salomon at Ecole Normale and also with Immanuel Bloch in Munich. So you can actually, these days you can actually image the fermions by using what is called the, quantum microscope. So you can actually image the positions of the fermions. And so you can actually image the real physical location of the eigenvalues of a GUE matrix thanks to this mapping. Okay, so we have been working quite a lot on this, connection between the GUE and the free fermion, and in collaboration with David Dean and Pierre Ledoussel and Gregory Scher. Here I'm not going to talk about that, but there's a interesting finite temperature generation. This is so far the ground state. You can ask what happens when I introduce temperature in this system, because real experiments, temperature is never absolute 0, so there's always a finite temperature. So we actually worked it out what happens when you introduce the finite temperature. So then you lose the connection to GUE eigenvalues, but still you can use some ideas from random matrix theory to compute the finite temperature properties of this fermionic system. Okay? But this is just a digression. So let me now go back to, yeah. Yeah. So, yeah, these two formulas are same. So
but there is no understanding of why.
What do you mean why? I'm just giving you a construction, explicit construction of the ground state. Okay.
As I said, because the formula are the same, but it
yeah.
doesn't tell you. What it would be in the quantum mechanics.
Yeah. So this is what I'm not explaining to you. So what is the point? The point here is, if you look really deeply, the fermionic system is actually what is called the determinantal system because of Wick's theorem. So you can write down any higher order correlation function as a determinant of two-point function, right? And this is exactly, so, this GUE is also a determinantal process. And in fact, what happens when you go to finite temperature, you lose the, you can actually write down the wave function mod square at finite temperature. It's no longer to a random matrix ensemble, but it still retains this determinantal property, okay? And using that determinantal property, you can actually compute many properties at finite temperature, okay? So for instance, this is a beautiful relation because, as we'll see, if you look at the rightmost, largest eigenvalue, right? So this is the Tracy-Widom distribution. I'll talk about that, okay, in the random matrix context. So in the fermionic context, this means at 0 temperature, if you look at the position of the rightmost fermion, this is exactly Tracy-Widom distribution. This is our precise prediction, which these people are, Immanuel Bloch's group is trying to measure. This will be a direct measurement of Tracy-Widom distribution. So you can ask what happens when I introduce temperature. Okay. So what happens is actually very interesting because the temperature, I'll talk about it maybe tomorrow a little bit if I have time. So at very high temperature, see what happens at very high temperature is that the Pauli exclusion principle doesn't exist, right? Thermal fluctuations. So effectively this term, it becomes very, very, small compared to the Gaussian. So essentially they behave like a free, just a factorized case again, independent particles, okay? So as a result, if you look at the X max, the largest position, rightmost fermion, this will be a Gumbel distribution, okay? So there will be crossover from Tracy-Widom to Gumbel as we increase the temperature. We have a precise form of that. And so this is what we are, trying to tell the experimentalists to measure, if they can. Okay, so let me sort of get back to the joint distribution again. And as I said, so this is a digression to a quantum problem. So I'm saying that you can interpret these lambda i's as the positions of fermions in a ground state of a, in a harmonic trap. Okay. Now, Now this one, as I said, that you could write down this Vandermonde to the power beta as e to the power minus beta over 2 log of lambda j minus lambda k, right? So then you see that this is exactly of this form of one-dimensional stat-mech system. I can interpret these lambda i's as the positions of the particles on a line, classical particles now, and they are sitting in this confining potential, which is this harmonic potential, and that they are interacting with each other. And here you see naturally, and because this product goes over all pairs of j and k, so this sum is also over all pairs of j and k. So this is a long-range interaction between all these particles. So you can think of this as charges they're sitting on a line. Now this log, of course, as Anupam mentioned already, this is a 2D Coulomb interaction, but here they are interacting, but they are interacting via 2D Coulomb interaction, although they are actually living on a 1D line, okay? And so this is a repulsion term, they are repelling each other all, and this is a confining term, which is trying to confine them towards the center of the trap, okay? So again, so you see that this factor beta, I can interpret this as a sort of inverse temperature, and this is exactly of the Boltzmann form with the energy function, which is precisely just this form. So in my example that I was talking about, general example, this g function, here is just the minus log. Okay. So, yes. Okay, so I'll just come to that in a minute. Okay, so why I scale it with n? Okay. Imagine that you didn't have this n, okay? Now, what's the physics of this? So, you see this, okay, let me just go to the next slide thing. Okay, so, yeah, maybe, okay, I'll go back here, okay. So, imagine that, okay, you didn't have this term, okay? Now, so this thing is trying to push them apart, and the quadratic term is trying to pull them to the center, right? So there's a competition between these two terms. And so we can estimate what is the typical scale of these two energy terms. So what is the typical scale of this term here? So if I didn't have this factor n, okay? So I have summation lambda is square. So this is the potential term. So this is typically will be, n times lambda typical square. Just to order of estimates basically, okay? Now, the interaction energy. So what is the interaction energy is this guy here, right? Now, how many such terms are there? They are over every pair. So this is n into n minus 1 terms, right? So that means typically the order of magnitude of the the interaction term is of order n square. So if they have to balance, if you have to balance these terms, so what you see is that n lambda tip square is of the order of n square, right? So that means typical lambda will scale like square root of n. Okay? So what I can do, so in order to make the eigenvalues of order 1, I can rescale, I can call it a new lambda I prime, which is old lambda I divided by square root of n. Okay? So once I rescale, then you see that this term, the potential term, now just becomes lambda I square. So in terms of lambda I prime, it just becomes lambda I prime square, sum over I. And the interaction term, which is minus log lambda I minus lambda j, so that doesn't change because, it's just lambda I prime minus lambda j prime by square root of n, times square root of n. But this log of square root of n is just a constant factor which comes out. You can absorb it in the normalization constant. So basically this is minus log of plus some unimportant constant. Okay? So once you rescale it, so now in the rescaled coordinates, the lambda I prime, there will be of order 1. That is that just so that the main idea is to make the lambda is to be of order 1. Yeah. Yeah. Right. No, but no, that's exactly what I said. So initially I said that, let's go back. Yeah, just by rescaling. So I mean, this beta is, you can put a sigma square here in the beginning, okay? And then I'm choosing this sigma square to be beta, so that I can write it as e to the power minus beta of these things, okay? It's just a rescaling, basically, nothing else. Okay. So this is the thing. So now I'm under this rescaling, so I already know that the lambda I is of order 1, okay? So what will the system do? So what the system will do is this repulsion is trying to spread them apart, and this potential is trying to push them down. So as a result, the system will settle down on an average for large n into a sort of in a region of space which is finite. It cannot go spread very far, because then that will cost too much potential energy, and it cannot come very close to each other because of repulsion. So it won't be a delta function, but it will some spread. And how far does it spread? So I want to calculate the density of states, basically. Now, so one thing before I proceed is that, so you have this term here, and so you see that again, I mean, this, you can write it this way. So I take out a factor n square and just write the energy as 1 over 2n summation lambda is square. Because the lambda is of order 1, so this sum is of order n, so this is the order 1 energy, and this is also of order 1 because of the n squared term here. So I can, just pull out a factor of n squared. So ultimately what I'm trying to say is that, this is just to set up the saddle point. Because if I, take out this n squared, everything here will be of order 1 in the large n limit. And then in the large n limit, I can just minimize this energy, and that will be the dominant configuration in the large n limit, which is also the same. Large n limit is exactly equivalent to large beta limit, right? I can keep n fixed and take beta to be very large, which is like a ground state. Okay, so the minimum energy is like the large n limit, if you like. Okay, ground state. And so to compute the density of states, so basically you want to minimize this and find out what is the configuration of lambda is that minimizes this energy, and that will be the dominant configuration that will dominate this partition function. So it's like we know that at 0 temperature, partition function is dominated by ground state energy, and here ground state energy, if you like, temperature going to 0 limit is like n going to infinite limit, because it always appears as this factor beta times n square. So this is my energy, and so in the large n limit, you can actually replace these guys by lambda square rho lambda d lambda, and log of lambda minus lambda rho. So where rho lambda is just the empirical charge density, right? So then the problem is to actually, so in the large n limit, so, and of course this guy has to satisfy the constraint that it should be normalized to 1. By definition, this is the fraction of particles between lambda and lambda plus d lambda, okay? And so what happens here is that the Zn, the partition function, is just, so if you do a saddle point, so this, e to the power minus beta n square will come out, and this will be just the saddle point energy. So you have to find the density of lambdas that minimizes the energy, okay? So I'll not go into the details, but if you do that, what you find is that in the large n limit, the density that minimizes this energy functional is what is called the Wigner semicircular law. Okay, so it's 1 over pi square root of 2 minus lambda square. So the charge density. So this is in the large n limit. I'm looking at the average density of states. How many eigenvalues are there on an average between lambda and lambda plus d lambda? And in the large n limit, what happens is that it concentrates onto its average, because it doesn't fluctuate very much. And so it goes from minus root 2 to plus root 2, with the density highest at the center of the trap, and in this harmonic well, and it goes to 0 as you go towards the two edges. This is in the strictly n going to infinite limit. Okay. Yeah. Sorry. Huh? Yeah, maybe, I don't know if I'll have time. Okay, so, okay. Maybe I'll try to do it tomorrow or something. Okay. So, let me just go a little bit ahead. So So, before you do any computation, so you can ask, what are these length scales in this problem, okay? So I have this average density of states, okay? So these are the positions of these charges, if you like. So there's a bulk. By bulk, I mean that near the trap center, okay? So here, I can ask, what is the typical distance between two neighboring particles, okay? How do I estimate that? So it's very easy to estimate. So what I do, I know the density of states. So this is just the fraction of particles between, let's say, 0 to L bulk, okay? So I just, integrate the density of states over a length scale L bulk, which I don't know, okay? And I set it to order 1 over n, right? Because it's just a fraction of eigenvalues. So if you take two neighboring eigenvalues, so rho lambda, d lambda, when you integrate, you just get 1 over n, okay? So now you just substitute this guy here, and you see that, in the large n limit, it's constant times d lambda, and that gives you the L bulk is of order 1 over n, which is, of course, quite physical because, you are just packing n particles in a finite region of space. So clearly, the typical interparticle distance between the bulk, deep inside the bulk, it will be order 1 over n. But the main point is that there is an interesting edge physics here because the density actually vanishes at the sharp edge √2 and minus √2 in the large n limit. So you can ask at finite but large n, what is the so density goes to 0, that means there are lesser and lesser particles, right? So they become sparser and sparser. So you would expect that the length scale between the particles near the edge is bigger than those in the bulk. And how do I estimate that? Again, I can do the same. This is called the Lipschitz argument. So again, you integrate from, let's say, it's just a heuristic argument, √2 minus L edge to √2. So I just, look at this thing and I set it to order 1 over n. And now you see, near the edge, it decreases like a square root. And this is very important. It goes like square root of 2 minus lambda over to the power half. So when you put it here and integrate, square root will give you a power 3 by 2. And when you reverse it, you will get that the L edge is of order n to the power minus 2/3, which is, of course, larger than the 1 over n for large n. Okay? So that means this typical separation, if I take a snapshot of my configuration of charges, okay, then the typical separation near the edge is much larger than in the bulk. Okay? And so you can ask, what happens for finite but large n? Can I actually calculate this average density? Okay, and this was actually done. It was done by Bowick and Brizza first, and then Forrester and many other people in the late 90s. And so this is the sort of, random matrix theory till the late 90s. I mean, not late, 90, 93, 94. And then something happened because it was already sort of, from these works, it was clear that there's something interesting we should go on at the edge of the semicircle, okay, as you approach this edge. And there should be a length scale n to the power minus 2/3. And maybe there's some universal physics there, okay? And then in the early 90s, so this was, there was a lot of excitement at that time, and then it goes on, that people started getting interested in the statistics of not just the average density of states, but just the statistics of the largest eigenvalue, okay? Lambda max. So now we know, for example, this has a physical, this thing also, it is just, it is just the position of the rightmost fermion in a harmonic trap at 0 temperature. But you can ask, what is the, this is a random variable. It fluctuates from one configuration to another configuration. And, what can I say about these statistics of this lambda max, okay? And so what do you expect? So again, this was explained by Anupam yesterday. So what you would expect is that the lambda max, on an average, we know it should be √2 because, this is the largest eigenvalue. On an average, its value is located here, okay? But it should fluctuate from sample to sample. And what is the scale of fluctuation? We have just seen that the, scale of fluctuations of lambda max would be the same scale as the separation between the particles, okay? So therefore, this should scale like L edge, and that should scale like n to the power minus 2/3, okay? So this is the mean, and this is the typical fluctuations. So I can ask, what is the distribution around that? Okay? Just like in this example of coin tossing, we saw that this was the mean, and the variance was square root of n in that case, and this was a Gaussian distribution. So here, again, you would expect that if I subtract the mean and scale by the width, which is n to the power minus 2/3, I should approach a scaling function. So in the case of coin tossing, this was just a Gaussian function. But here, in this case, it's a non-trivial function. And this non-trivial function is all because of this fact that you cannot factorize. This is a correlation. It comes from interaction. And this is what was computed by Tracy and Widom in '94. And what they showed, this I'm not going to repeat. Anupam had shown you that, it satisfies some complicated Pan-Levet-2 equation. And so this is a non-trivial scaling function. And I'll finish in 2 minutes. So if you plot this function, so it looks like Gaussian, but it's not quite Gaussian, okay? So it depends on beta. So it varies from beta equal to 1 to 4. And it has the asymptotics, which is that for large negative x, it actually goes like exponential minus beta over 24 mod x cube when x goes to minus infinity, and when x goes to plus infinity, it goes like x to the power 3 over 2 with the coefficient 2 beta over 3, okay? So it's highly non-Gaussian. And so you can say, okay, so what? Okay, you calculate exactly some distribution of some largest eigenvalue, but who cares, okay? And in fact, this is what happened. After '94, for 5 years, it stayed dormant. Nobody paid much interest to it. And then something happened in the late '99. There was a beautiful paper by Bike, Dybdt, and Johnson, who actually first, okay, I don't have time to go through that, but they showed that there's a beautiful problem called Coulomb problem in combinatorics, which they could solve exactly, and showed that this is also has Tracy-Widom distribution. This is called the longest increasing subsequence problem. It will be another talk. I cannot go into that details. But then, since there was a rapid development in the in the last 20 years, both in the physics and maths literature, so now we know that the same Tracy-Widom distribution appears in many different models, from directed polymer to this random permutation, then KP's equation. If you take the Kardar-Parisi-Chang equation of interface, and where the height of an interface evolves stochastically, and you can ask what is the probability distribution of the height. So it turns out that is also given by Tracy-Widom distribution. So some of these problems have direct link to random matrices, but some of them a priori have no links to random matrix theory. Okay, so for example, some of the liquid crystals and then sequence alignment problems, you don't see where is the random matrix coming in. But nevertheless, this Tracy-Widom kept appearing everywhere. It's somewhat like this Gaussian distribution of central limit theorem, and it just kept on popping up in many different fields. And I'll probably mention some of the quantum cases in the quantum quench problems that Andrea was talking about. So there also it appears, and it just appears in many unexpected places. And it has been measured in many different experiments. So this is the turbulent liquid crystals, this is the coupled lasers and disordered superconductors and so on. So, and as Anupam also mentioned that, you can find some popular science articles where they discuss about the ubiquity of the Tracy-Widom distribution, okay? So now, I'll just finish this and then I'll stop basically. So now, okay, so there's two things. So we now know that lambda max, should fluctuate around its mean value on a scale of n to the power minus 2/3, the typical fluctuations, okay? But the atypically large fluctuations, so this is on a scale of n to the power minus 2/3. But if I'm interested in the scale of fluctuations of order 1, obviously, like in this problem, they are not described by Tracy-Widom distribution. Just like in this problem, they are not described by Gaussian. So you'll have large deviation tails. And what can we say about these large deviation tails? Now, why is it important? And this is where I want to connect up with the question I asked in the beginning. So you see that when I asked that the probability that all the eigenvalues are negative, okay? So this is this famous random May problem. So this is the probability that the largest eigenvalue is negative. Lambda max is less than or equal to 0, right? Now look at this curve here, distribution of lambda max. Lambda max typical value is √2. So if I want to know what's the probability that lambda max is less than 0, I'm really looking at the extreme left large deviation tail, okay? So to answer this question, you need to study the large deviation tail. Just like in the Gaussian problem, if you just put in the Tracy-Widom distribution, if you just put, in this example here, a Tracy-Widom distribution, if you take the Tracy-Widom distribution and put W equal to 0, you won't get the right answer because Tracy-Widom describes typical fluctuation is not valid at the large deviation tail. So if I want to answer this original question, I need to really look at the large deviation tail. Okay, so Tracy-Widom is not enough. So this is, so we have to, and this is why you see the why the large deviation is necessary. And I'll talk about tomorrow, I'll talk about both tails. And similarly on the right tail, this is a right large deviation tail, and we'll see that, that they are quite different. And so this is number one motivation, that why we are interested in large deviation tail. And number two motivation, and then I'll stop, is you can ask yourself that why is Tracy-Widom distribution so ubiquitous? Why do we see it everywhere? And as I said, some problems you can map it to random matrix theory, but other problems not. So this is my last slide. And if you are a statistical physicist, you have learned in your course that that there's a near critical phenomenon. Whenever you are near a critical point, there is universality, because if there is a phase transition, often there is universality. And because the details, the microscopic details becomes irrelevant near a critical point. So a natural question then is that, can you associate Tracy-Widom distribution to some critical phenomena, to some phase transition? Okay. So this is the question, and maybe that might be useful to explain why is it so ubiquitous. But then the questions are where to look for a phase transition. I have a PDF of lambda max. Where to look for a phase transition? Where is the critical point? What is the control parameter? What are the two phases? Okay. So this is the question, and this I'll discuss tomorrow. Thank you.
So could you so you have made the relation between the eigenvalue of this JOE ensemble and the Coulomb gas.
Yes.
So could you extend this analogy to dynamics? For instance, if you take an Orstein-Lundbeck process or something like that for the entries of your matrix, yeah, would it give you a Brownian dynamics?
Yeah, exactly. So this is what is called the Dyson-Brownian motion, actually. So if you take, for example, your matrix entries as a Ornstein-Lundbeck process with a fictitious time t, okay? Then what you know is that in the long time limit, the entries are all going to Gaussian distributions, right? The stationary states of these guys. So now you can ask, okay, but at a finite time t, this is no longer, it's not in the stationary state. And you can ask, okay, at each time t, if I diagonalize my matrix, I'll get these eigenvalues lambda 1, lambda 2, lambda 3, lambda t, lambda n. And what is their dynamics? Okay. So the dynamics of these lambda is, so basically, as Freddie was saying, so if you take your n by n matrix, and imagine that you say that, your entries xi, j, t, so they are doing Ornstein-Lundbeck process. Plus some noise. Okay. So here this time t is a fictitious time. So just introduced by hand, and now you take, all you know is that the probability distribution of xij, the entry. So this is in general time dependent. So this will be exponential minus xij square over 4d1 minus e to the power minus 2 mu t, something like that. Okay. So in the long time limit, it approaches to time independent stationary Gaussian form. So this matrix ensemble, which is now t dependent, okay. So in the long time limit, it goes to GUE, okay. But I can ask at a finite time t, okay, I can diagonalize for each time t, at each instant of t, I can diagonalize this matrix, and I'll have n eigenvalues, which are time dependent now. So can I study the dynamics of these eigenvalues, okay? So indeed you can. In fact, the equation, what you can show is that starting from these equations of the entries, after diagonalization and using second order perturbation theory, you can show that this will be minus mu times lambda I plus beta by 2, 1 over plus some other noise. Okay. So what this says is that you have, think of these lambda i's as a function of time t. So each of the eigenvalues will propagate in time. but they will never cross each other because of this term here. Because if you start from this, there's repulsion. This is a repulsion term, okay? So they will never cross each other, and they are sitting in an external potential. And of course, if you take at very long time t, and if you ask what is the joint distribution of the eigenvalues, so from this you can calculate the joint distribution of eigenvalues at any time t in principle, and then long time limit, it does approach to Vandermonde form.
So this dynamics you get is an overdamped dynamics.
Sorry?
The dynamics you get is overdamped. You have no inertia. It's overdamped.
No,
It's overdamped. You have no inertia.
overdamped, yes. Overdamped, exactly.
So is there a way to generalize this with a dynamics which is...
It's underdamped or something, so you want to second order.
Inertia.
Yeah, because the way you derive this equation, okay, here. Because this is, you don't assume that it's overdamped. You actually derive this equation starting from this, okay, by second order perturbation theory, okay. Now, to generate this lambda double dot term, it's not easy, at least within the quantum mechanics context, it's not easy to see. Operator linear algebra construct, how to generate a second order term, okay. But in fact, this is a good comment because, if you want to derive the joint distribution of eigenvalues, one way is to do this Vandermonde term, but it's very hard, okay. And this very hard means once somebody does it, it's easy, but it's not so easy. But one nicer way of deriving this result is to look this Dyson. This is generally called the Dyson-Brownian motion. So here, if I give you this, right? So immediately you see that in the long time limit, because this is just a potential term, right? So you can write down this as minus del u del lambda I plus xi I of t. And so you immediately know that the stationary state of this will be exponential minus u of lambda I, right? So you see u of lambda I will be lambda I squared plus log of lambda I minus lambda t. Okay? So that tells you the stationary states of this has precisely, of the eigenvalues, has precisely this distribution. And this is the easiest way of deriving this, instead of making this change of variable and going to Jacobian and so on. So this is another way of deriving, and often it's simplest. So by the way, the fact that you can actually derive the joint distribution of eigenvalues, this holds only for rotational invariant ensembles. For example, if I just give you uniform distribution for each entries, okay, independent but in uniform distribution, and I ask what is the joint distribution of the eigenvalues, nobody knows. Okay, so because once you lose this rotational invariance, you don't know how to compute that. You can actually, so what people do is often they write down the corresponding, Dyson-Brownian motion, and then numerically evaluate what is the stationary state and so on for these non-invariant distributions. Okay, so because there it's very much harder to calculate the stationary state of the joint distribution of the eigenvalues.
One question related to this again. So you said second order perturbation theory.
Yes.
It's exact, right? This one.
It's exact, yes. Second order perturbation theory in the delta t, the noise, this thing. So when you go in the continuum limit, you take the delta t going to zero limit, so you don't need the higher order terms, basically. Yeah.
The other question was so in the quantum case, instead of harmonic potential, if you
Yes.
have other potential.
Yes.
And also, of course, you still have the determinant thing, but typically.
No, you cannot calculate this. You cannot calculate this.
So typically you can't calculate. Is there an example where you can't? There's no other example where.
I don't know any other example. Harmonic is the. There is another one which you can do, which is the hard wall. Basically, you take a box potential. So there, actually, you can compute the joint distribution. You can calculate the psi naught x1, x2, x3, xn, and there it's related to what is called the Jacobi unitary ensemble, which is also known in random matrix theory. So JUE, not GUE. Okay. But if you tell me, if you ask me that given the quantum trap potential, what is the, is there a classical matrix potential I can write? There is no one-to-one correspondence, basically. Sorry?
Is there anything known about the largest eigenvector?
So again, in the rotationally invariant ensemble, you see the eigenvectors, they completely decouple. So basically, if you take any eigenvector, so all the elements are completely random except that their sum of square is 1. Okay. So the largest, largest eigenvector associated largest eigenvalue doesn't make any sense because they completely decouple. Okay. So eigenvector sector is totally different, And essentially, eigenvector doesn't know about the eigenvalue, basically.
This other thing is like for this Ornstein-Uhlenbeck process.
For the?
No, this one, that Ornstein-Uhlenbeck process where this xi's are Ornstein-Uhlenbeck.
Right.
So I guess this matrix is still Gaussian. So isn't it just that at any time?
Yes.
Lambdas are scaled with just, because I know how xi scale with time.
Yes.
So lambdas are, will also similarly scale, right? I can still write down the joint distribution of all the lambdas.
No. I mean, no. At a finite time t, the joint distribution of lambda 1, lambda 2 will have a much more complicated expression. Only in the long time limit, it will approach this.
But isn't it just
lambdas are not Gaussian, right?
No, lambdas are not Gaussian.
Yes.
Xi's are Gaussian.
Xi's are Gaussian, yes.
So now it's, at any time, it's still a Gaussian orthogonal matrix.
Yeah, that is the whole idea, that you can diagonalize at any time t.
Exactly, but do I need to diagonalize at any time, or I can just look at the joint distribution at the initial time and just rescale the...
No, you cannot rescale. No. Because, I mean, see, basically the diagonalizing vector, this S vector, orthogonal matrix that you use to diagonalize, that is also time dependent. That varies from time instant to time instant. So if I diagonalize at time t by some vector, okay, the eigenvectors are also time dependent, right? So next time step, it will be different matrix which will diagonalize. That's why you need the second order perturbation theory. No, you cannot just simply rescale things, no.